Inside every human body lies a hidden landscape of water molecules, spinning in silent choreography. For decades, peering into this flesh and bone reality required slicing open tissue or exposing patients to damaging ionizing radiation. Medical diagnostics remained largely trapped in two dimensions, reliant on shadowy density maps produced by conventional X-rays. What if an entirely different physical phenomenon could translate atomic spins into crystal-clear images of living anatomy? In September 1971, a young research chemist named Paul Lauterbur sat at a modest workstation at Stony Brook University. He was watching a routine experiment involving nuclear magnetic resonance, a technique known as NMR that scientists use strictly to determine the chemical composition of liquid samples. The existing machinery immersed samples in a perfectly uniform magnetic field, yielding a single sharp spectrum of energy absorption spikes. Lauterbur realized that this quest for absolute uniformity was actually hiding spatial information. The foundational spark occurred when Paul Lauterbur recognized that introducing deliberate irregularities into the magnetic environment could revolutionize raw data collection. By deliberately superimposing a secondary, linear magnetic field gradient across the primary field, different parts of a sample would experience slightly different magnetic strengths. Because atomic nuclei absorb and re-emit radio frequency signals at precise frequencies dictated by their local magnetic field strength, spatial position could be mapped directly to radio frequency. Testing this radical concept required a physical subject far simpler than a human patient. Lauterbur constructed a crude prototype consisting of two thin glass capillary tubes filled with ordinary water, submerged within a small vessel filled with heavy water. He then placed a tiny hard-shell clam inside the chamber to introduce complex biological structure. The resulting raw signals, collected from multiple angles as the gradient field was rotated around the sample, contained the very first spatial map produced by magnetic resonance. By applying mathematical algorithms similar to those used in computerized tomography, Lauterbur reconstructed these one-dimensional signal profiles into a rudimentary two-dimensional cross-sectional image. He initially named this groundbreaking technique zygmatography, derived from the Greek word for joining, symbolizing the union of magnetic fields and radio waves. It was a crude, low-resolution black-and-white grid, yet it clearly demonstrated that liquid water variations within biological tissues could be visualized without harmful radiation. When Lauterbur submitted his visionary findings to the prestigious journal Nature in late 1972, the editors promptly rejected the manuscript. They argued that the images were blurry and that the practical applications of turning an established chemical analysis method into a spatial map were far too speculative. Undeterred, Lauterbur insisted on a second review, emphasizing that his technique unlocked an entirely new window into physical matter, eventually persuading the journal to publish his landmark paper in early 1973. Across the Atlantic Ocean, physicist Peter Mansfield at the University of Nottingham was independently exploring similar quantum principles. Mansfield realized that while Lauterbur's method could create images, gathering the data point by point took far too long for clinical viability. A patient remaining completely motionless for hours was an impossibility. Mansfield developed a mathematical breakthrough using fast Fourier transform analysis and slice selection gradients, demonstrating that magnetic signals could be captured and processed in fractions of a second. The underlying physics operates at the quantum scale, governed by the inherent angular momentum of hydrogen nuclei. Because the human body consists predominantly of water and fat, it is densely populated by hydrogen protons, each acting like a microscopic spinning compass needle. Under normal conditions, these nuclear spins point in random directions. When a patient enters a powerful static magnetic field, these protons align parallel to the field lines, precessing at a precise frequency proportional to the magnetic flux density. By 1978, Peter Mansfield had designed a larger, highly customized magnetic coil system capable of accommodating a human subject. To prove the absolute safety of his rapid spatial acquisition methods, Mansfield volunteered to be the first human inserted into the tight, humming machine. Despite widespread fears that high-frequency radio pulses might generate dangerous electric currents within human flesh or distort cardiac rhythms, the experiment was a complete success, producing clear cross-sectional images of his abdominal anatomy. Engineering a commercially viable system presented staggering physical and technological hurdles. Generating stable magnetic fields required massive electromagnets cooled by liquid helium to near absolute zero, entering a state of superconductivity where electrical resistance drops to absolute zero. Furthermore, the gradient coils that rapidly switched magnetic fields created intense mechanical forces, resulting in the violent, rhythmic knocking sound that remains a signature characteristic of all modern diagnostic scans. As the technology moved closer to hospital operating rooms, a critical non-technical barrier emerged in the minds of clinicians and patients alike. The original nomenclature, nuclear magnetic resonance, contained a word that sparked immediate anxiety during an era dominated by Cold War nuclear fears. Hospital administrators worried patients would refuse tests, mistaking them for radioactive treatments. Consequently, the medical establishment systematically dropped the word nuclear, formally establishing the name magnetic resonance imaging. Medical adoption proceeded with caution as mainstream radiologists accustomed to traditional film X-rays initially met the new technology with profound skepticism. Doctors struggled to understand how soft tissues, which appeared uniformly gray on X-rays, could yield rich contrast differences without invasive contrast dyes. Early advocates had to demonstrate repeatedly that subtle variations in tissue water content, relaxation times, and proton density could highlight pathology with unprecedented sensitivity. Early clinical trials soon provided undeniable proof of the machine's revolutionary diagnostic potential. The device revealed subtle brain lesions, early-stage multiple sclerosis plaques, and soft tissue spinal injuries that had previously been completely invisible prior to surgical exploratory procedures. Unlike computed tomography, which relies on hazardous X-ray beams, this new approach yielded exquisite soft tissue differentiation without depositing ionizing energy into living cellular structures. Over the subsequent decades, the basic platform underwent extraordinary technological evolution, moving from low field strengths up to powerful superconducting magnets, generating 3 Tesla or more.
Researchers introduced functional magnetic resonance techniques capable of measuring real-time localized changes in blood oxygenation levels. This allowed neuroscientists to map human brain activity as subjects thought, spoke, or experienced emotions, transforming cognitive research alongside medical diagnostics. At its core, the physical interaction remains a masterclass in controlled quantum resonance. A brief pulse of radio frequency energy at the exact Larmor frequency tips aligned hydrogen protons away from the main magnetic field. As the radio pulse ceases, the protons relax back into alignment, emitting a faint radio signal of their own. Gradient magnets continuously alter the local field, ensuring that the precise frequency and phase of these echoes encode exact spatial coordinates in 3-dimensional space. To overcome the immense computational load required to reconstruct raw frequency data into 3-dimensional volumes, engineers developed sophisticated spatial encoding routines. Mathematics transformed chaotic radio echoes into crisp digital representations of cartilage, gray matter, and vascular structures. What began as a time-consuming mathematical experiment transformed into high-speed, real-time imaging systems capable of capturing the beating motion of a human heart. Today, tens of thousands of these diagnostic machines operate in medical facilities around the globe, performing millions of scans every year. Modern medicine relies on them to diagnose stroke, evaluate complex spinal traumas, detect early-stage cancers, and guide delicate neurosurgeries. The ability to non-invasively differentiate between healthy and diseased soft tissue stands as one of the most significant technological leaps in the history of human healthcare. The future of this diagnostic field continues to expand toward ultra-low field, highly portable scanning units enhanced by artificial intelligence reconstruction algorithms. These compact systems promise to bring advanced imaging out of specialized radiology basements directly to remote clinics and emergency vehicles. Yet every sophisticated machine produced today still relies on the exact spatial encoding principles conceived over half a century ago. Looking back at the genesis of magnetic resonance imaging, we trace a direct line from high-level theoretical physics to a humble 1971 experiment with a clam at Stony Brook University. The combined genius of Paul Lauterbur and Peter Mansfield forever altered how humanity perceives the living body. By transforming an obscure chemical technique into a spatial window, they unlocked a non-invasive view into the human form, turning invisible quantum mechanics into a light that guides modern medicine.